is this? What are you doing? All right, can everyone hear me? So there's about like a 10 or 12-second delay, so I might have to wait a second before I actually see your comments. So yeah, if you're looking at this one here, speed of sound is just going to be 343 meters per second. So one question that I've been seeing a lot is this going to last until April 3rd? Yes, it's going to be online teaching until April 3rd, and honestly, it might go longer than that. That's just by April 3rd, the district is going to reevaluate if you go back. It's not we are going back on April 3rd. So this could possibly last longer, and all field trips through April 30th have been canceled. So yeah, it's going to be pretty much online like this. So what I'm planning on doing is each day I'm probably going to be going on at a set time. For now, I'm liking going on at 10 and really getting started by 10:30. And then all of your assignments will be due on Google Classroom. Yeah, no AP study sessions, no anything. Like every single district event has been canceled through April 30th. We don't know if summer is going to start on the same day. I don't think summer is going to be delayed more than a week at most, but I haven't heard anything official. I'm still getting paid to work right now, so I don't think the school is going to want to pay every single teacher for an extra week into the summer. So there might be some special circumstance where we're out on the same day, but we don't know. I'm still waiting to hear from that. I have a staff meeting at 1 today online, and we'll probably hear a little bit more information that I can relay to you. It's funny that you recognize it as Connects. I mean, they're really useful. I was able to build this stand pretty fast. My setup is actually pretty ridiculous. I went to go stream on my iPad, but apparently I can't stream from a mobile device if I don't have 1,000 subscribers on YouTube, so I tried to stream from my laptop, but it's an older version of Linux and that wouldn't work. And then so I have my Linux laptop up, my iPad streaming to my gaming computer, which is Windows 10, which is streaming to YouTube, and then I'm watching it on my computer in here. Yeah, everything is going to be turned in online. I made a assignment for every individual thing. So your warm up, you'll work it out. You'll take a nice clear picture that I can easily read, and you'll post that on Google Classroom. My computer, it's a i7 7700K processor, 16 gigs of RAM, DDR3 or 4, I think 4. Then I have a GTX 1070, 1 terabyte solid state hard drive. A lot better than this garbage laptop I'm using. Any other quick questions about how class will work or what's expected or anything about the shutdown in general? Test corrections, I'm probably just going to curve all of the tests. I really don't know what else I could do. So I'm probably just going to curve the tests and just call it at that. So I'm sorry for the people who've been working on it. You'll be better off for the final exam. But yeah. So the time markers, I'm going to disable comments after this video goes up for the bottom part. You'll still see the chat on the side. So what my AP class did, someone must have written it down in a text document and then they posted it as an announcement on Google Classroom. That would be really nice. Yeah, no way to retake tests. It's just going to get curved. I don't see any other way to do it other than that. Your quiz that you have, the online quiz, I put an announcement up. You can take nice clear pictures of that, post it on Google Classroom, and then I can grade it. Late work, yeah, that's a good question. I'll put up different assignments for each late work, and you can take pictures of it to get it turned in. Tests and quizzes, probably just through Google Classroom. Yeah, that's just how it's going to have to be. So the time markers would be probably a good time marker would be when we start the warm-up. We're going to go through specific examples in your textbook, so you could write the question number from the textbook next to the time markers. And I'm also going to take a few questions about the quiz, so you can write what quiz question we're talking about at which time. So yeah, keep asking questions. The online textbook is the exact same one we normally use. Work on your warm-up for now. I'll start working through the warm-up at about 10:30. And then you can keep posting questions and I'll keep answering them as you have them, but try to work on the warm-up for now. And also, yeah, pull up your online textbook because we will be going there. Pull out your take-home quiz. We'll be working on that a little bit. Uh, yeah, warm ups. So pretty much every single assignment that you have that's on paper, you're going to take a picture of it and post it into Google Classroom under the announcement. So under the warm up tab, under the warm up announcement, you'll actually take a nice, clean, clear picture, like one picture per page that's easy to read, and you'll post that on Google Classroom, and I'll put each warm up as a small grade. Like, probably it's going to be about a tenth of a binder grade type thing. Uh, yeah, if you left your things at school, if you ask for specific assignments, I can post them. Um, I really don't know if school is going to be shut down for the rest of the semester. Honestly, my best guess is the CDC was saying an 8-week quarantine. So probably about 2 months. So if I'm completely guessing here, this is the district hasn't said anything. Don't take this as official. This is a complete guess on my end. But I would assume if we come back for the year, it's probably going to be late April or early May. But again, I could be very wrong about this. We might come back sooner. And yeah, there's a really good chance that seniors aren't going to have a graduation. Even if we do come back to school, I think there's still a chance we don't have senior graduation. But yeah, there is a decent chance that no one goes back to school. Even College Board is talking about possibly some way doing the AP test from home. That's how you kind of know it's a little bit serious. Prom, again, pretty sure there isn't going to be a prom. I could be wrong, but yeah, I think pretty much every extracurricular thing is going to change this. Yeah, it's definitely one of those things when you look at it, kind of the whole point of what we're trying to do right now, and you may have heard the term flattening the curve. So it's either a lot of people are going to get sick at once, and then a lot of people will be severely ill in the hospital, and the hospitals can't handle it. So kind of the whole goal right now is to spread out the amount of time that people are infected for, so we have fewer people at any given time, but that also means it's probably going to last a little bit longer. So that's kind of the whole goal of this strategy, is to make the virus last longer, which is why we're probably going to be out a little bit longer. I don't think people are overreacting about COVID-19. Most of you are actually really safe. People under the age of 18 have barely been getting sick. The biggest problem is the people who get severely ill end up in the hospital with really bad bacterial pneumonia, and they need ventilators and ICU beds, but we just don't have enough of them. So the problem is going to be, if a lot of people get really sick at once, they're going to be picking and choosing who gets to live, who gets to die. So it's just kind of one of those things. We're trying to make sure that a lot of people don't get things. I wouldn't stock up on everything. I wouldn't go and hoard food, but I think it would be good to, each time you go to the store, just get a little bit extra. I have a extra week of food and everything. Did I not put the actual quiz on Google Classroom? But yeah, I have a little bit of extra supplies. I have supplies in case something goes crazy, but I'm not trying to doomsday prep or anything. Alright, so I uploaded the quiz. um, the water, honestly, you could just take a bunch of tap water. I don't think the water is going to be an issue for this one. I don't think food is going to be more of an issue. Like it, again, these are good things to have, but I wouldn't start stockpiling like the world is going to end. It's not quite to that point. I like how you chose sandpaper over any other type of paper. So West, you're going to have to kind of decide. I mean, normally we call East positive and West negative. I would draw out the pictures though. Yeah, I was expecting people to forget things. That's kind of why I started with the Doppler effect. So yeah, I can give a kind of recap. So first of all, let's kind of look at our Doppler effect equation. So our Doppler effect is going to be the frequency detected, or whatever frequency is heard, is going to be equal to the frequency of the source times the speed of the wave plus minus the speed of the detector divided by the speed of the wave plus minus the speed of the source. All right, so we have this. And then again, the key words we're looking for is the object going toward the other object, or is it moving away from the other object? If one is going towards the other, I expect frequency to go up. Frequency or pitch, again, pitch and frequency are the same thing we're talking about. So if it's moving towards the other object, I expect that to cause pitch to go up, frequency to go up. If we're going away from an object, I expect frequency to go down. So this is how we're going to be deciding plus or minus for each of these. I guess I'm just normally the type of person that buys a lot of toilet paper at once because I'm too lazy to keep going to the store. So we already kind of had a little bit of a supply. Not towards for numerator. Oh, well, yeah. Or you're actually starting to solve this. I'm still going to give you about 5 minutes to keep working through this before I actually go through and solve it. I don't know about grade lock and corrections yet. Um, yeah, that's just the thing I don't know. I'll figure out about that hopefully today. Yeah, today at 1, again, we have an online meeting, and hopefully I figure out some more information about grades, the 6 weeks. Is it going to be the same amount of time or extended? But yeah, I don't know answers to that yet. I do know in Skyward it's saying that I'm not supposed to post grades this week, but it says I can post grades next week. So I'm assuming if anything happens, if any of the schedule changes, everything would be shifted back by a week, but I don't think it's going to be more than that. 343 meters per second is just a typical room temperature speed of sound. I just gave that to you. It's also on the formula chart. If you're not given anything about temperature or speed of sound in the air, you can just use that 343 meters per second. So 332 meters per second is the speed of sound at 0 degrees Celsius. So the speed of sound at a certain temperature is going to be 332 meters per second plus 0.6 times whatever temperature it is in Celsius. So yeah, so it would be 332 meters per second if our temperature is 0 degrees Celsius. Um, I like games. I mostly like RPGs. The game I was playing over the break is Wasteland 1. It was one of the biggest early CRPGs. It was made in 1988, and they just recently released a remake of it, and so that was good. But yeah, anything with RPG that has a ridiculous amount of stats to figure out are kind of the games I like. I'm not anything like a first person shooter gamer or any pretty much Twitch shooters I'm not so great at, but yeah. Yeah, I've been meaning to play Divinity. It's one of those things that looks pretty interesting. I just haven't had time to get around to it. Another game I've been meaning to play a little bit more is XCOM. But probably the next things I'm going to play through are the original Fallouts 1 and 2. uh, I could stream on Twitch, but I think I'm good. Story action games. Yeah, if I play any game that is action, I definitely want to be affecting the story. Um, yeah, I'm excited about Wasteland 3. I like the second one, which is what kind of got me into that, and Wasteland was the game that kind of inspired Fallout. Uh, you can actually do a lot with Kinects. I actually have a TV antenna that I built with a bunch of copper wire and Kinects. I just, anytime I need something kind of non-standard built. I just build something out of them. Yeah, they may have given it away for free. I like the company that's making it. At least they recently got bought out by Microsoft, so I actually didn't mind buying and supporting them because they were a small studio. So I didn't mind actually paying for it. But yeah, if you want to see the TV antenna, I like completely built it from scratch. And I even included a radio reflector on the very back of it, where there's wire mesh. And so I figured out the size of the wire mesh based on the wavelength of the radio waves that are sent out to the TV. It's kind of like a microwave, how in a microwave you have those little holes. The holes are just big enough to block the microwaves without them going through. So same thing with my antenna. I could do a face reveal, mostly because I got a haircut, but that's about it. I didn't say anything about getting a haircut. Are you imagining things? Yeah, 70 subs. I had a channel with 700 subs until YouTube didn't like my bot and just deleted me without any strikes. So that's when I found out it's not always 3 strikes. Um, the thing I like about teaching in class is you can ask questions immediately. On here, I have to wait like 10 or 15 seconds to actually see your question. But I will say I kind of like the live stream in the sense that for AP, I have 4 AP classes, and I just did the live stream once. That was really nice. For me, honestly, I kind of like building things, so I didn't mind setting up this whole setup. I like disassembled part of a monitor, connected it to my laptop. So I like building things, so that part was actually fun. And then it's nice just teaching kind of one class, and then I'm sure you like just looking at a video where you can kind of go back through each and every time. So I like doing this from home as long as we don't have to extend the school year. That would be pretty obnoxious. Lego. My brother was a Lego person. He had a lot of Legos. I had some. I always liked Connects because I felt like I could build useful things out of them, as evidenced by my antenna and stand right here. So even though this isn't an official spring break, uh, you aren't actually supposed to start yet. I'm kind of jumping the gun on this. Please don't get me in trouble for that, but I just don't want people to fall behind more. So that would be why we might extend the school year. I'm leaning towards, because it's such special circumstances, I think they won't extend the school year, but if they did, they might extend it by a week. And that would be annoying. Yeah, our summer would be shorter. All right, so yeah, I've given you some time to look at the warm up, even though I've been distracting you. Uh, so the toward or away from, it's for either the source or the detector, both of them. So if the detector moves toward the source, or if the source moves toward the detector, we're going to hear a higher frequency. If the source moves away from the detector, or the detector moves away from the source, we're going to hear a higher frequency, or lower frequency, sorry. Uh, yeah, I don't. There's really no way they're going to do any sort of online learning for these classes because they don't have any sort of curriculum for this. So no matter what they say, I'm going to be on my own anyways, which is why I just said, like, forget it. I'm just going to start now. But yeah, online instruction. It sounds like it's probably going to be more your teachers. So when we have the meeting today, I might end up shifting around the times I do these streams to not interfere with other people. But yeah, probably something like that. So, I mean, honestly, if you know what you're talking about, you can shift anything to online. Like, I was too lazy to even go to campus on Monday. We had a 2-hour interval, but I kind of knew what we needed to do, so. Um, yeah, if they extended the school year, they might have exceptions for seniors. But yeah, I'm leaning towards they might not extend the school year. It's serious enough to where they just completely cancel the STAR exam and EOCs and everything. So based on that, they might just say it's okay if the year is a little bit shorter. I think I'm leaning more towards they're probably not going to extend it, but just kind of keep that possibility in your mind that it might be extended. Just like they say they're coming back April 3rd, or they say they'll reevaluate April 3rd, just keep that possibility in your mind that it might be a month after that, or you might just never go back. At least for this year. Alright, so let's stop getting distracted and actually look at the warm up. I had this pulled up. Yeah, three was intended to be a tricky question, so we'll get to that in a second. All right, so number one. So a passenger train moves 70 meters per second west. All right, so the passenger train is moving, did I say 70? 40 meters per second west. The horn produces a frequency of the source is 650 hertz. Find the frequency each person below would hear. So one, a stationary person in front of the train. So they're over here. In front of, on the side of the train, not about to get hit by a train. On the road, standing next to the train. So our detector, is not moving. So that leads us to set up our equation. So frequency heard by the person is going to equal to, the train puts out a 650 hertz sound, times speed of sound. We're going to use 343 meters per second. I'll either give this to you, or you'll be given a temperature to be able to find this. All right, so the top speed of our detector, so our detector is not moving, so it doesn't really matter plus or minus 0, it doesn't change anything. But our source is moving at 40 meters per second. And the source is moving toward the person. The person is in front of the train, so the source is moving toward the person. So we see toward. If I see toward, I expect frequency to go up. But because we're in the denominator, in order to make the frequency to go up, in order to make this fraction bigger, I need to subtract. So negative, exactly. And then make sure when you put this in your calculator, put parentheses around the denominator. Don't put in something like this. If you put in something like this, then your calculator is going to do the division, and then it will subtract 40 afterwards. So whenever we do this, either actually put it in parenthesis form or put it in your calculator like this, where you have parenthesis before and after the subtraction. And you should get 735.8 hertz. All right, question 2. Now the person is stationary but behind the train. So if they're behind the train, so our detector is over here at rest behind the train, so the train is over here going away from them, going west at 40 meters per second, and this is our source. All right, so our source is going west at 40 meters per second away from our detector. So we're going to have a very similar equation here. 650 hertz. Again, 343 meters per second for our speed of sound. Again, our detector is in the numerator. Our detector is not moving, so 0. And our source is 40 meters per second. And then, like you said, so this one is moving away from, and I don't think you can see that far over. There we go. Away from. So if we see away from, I expect frequency to go down. And so exactly like you said, because frequency is going down, I need a bigger denominator in order to make this whole fraction smaller. So bigger denominator makes the number smaller, so we get a lower frequency. And you should get something about 582.1. All right, three was one that I intentionally put on there to make you think a little bit. So 3 wants to know the frequency heard by the passenger on the train. So, is the passenger sitting in front of or behind the train horn? I think this is kind of an obvious question. Normally the passenger is sitting behind the front of the train, right? So let's draw our train right here. Moving west at 40 meters per second. Still 650 hertz. And then we have our passenger here, which is our detector. They're moving at the same speed as the train unless something went horribly wrong. So we can put this in. Frequency detected, 650 hertz. All right, 343 meters per second, 343 meters per second. Both the train and passenger are going at 40 meters per second. Now, there's no relative motion between these objects, but I'm still going to kind of use the words toward or away from. So again, numerator, we're talking about the detector, so we're looking at our passenger. Now, the passenger isn't really moving towards the train itself, but it's moving toward where the sound came from. The sound came from right here and is going out. The passenger is moving into the sound. So we could say the passenger is moving toward the source of the sound, or the sound itself, even though they're not getting closer to the front of the train itself. So I'm still going to call this toward. So because this is moving toward the source of the sound, then I'm going to expect frequency to go up. And so if frequency goes up, I expect my numerator to get bigger. A big numerator means a big fraction. Now, the train itself, again, the train isn't moving relative to the passenger, but the train moves and then emits another noise, So each wavelength is getting stretched out this way. So even though the train and passenger aren't moving towards each other, I could say that the train is trying to move away from the passenger. Right? Away from, towards. So away from means I expect frequency to go down. If frequency goes down, I expect a bigger denominator. So obviously, this divided by this just goes to 1, right? This is the same thing divided by the same thing is 1. So the frequency detected is going to be the exact same frequency put out. And the easy way to kind of think of this and get it right, we didn't even have to do any math. We could just imagine, hey, these two things are going the exact same speed in the exact same direction, so the effect is probably going to cancel out. It's probably just going to end up with the exact same frequency as before. All right, so we have 4. Now we have a person driving west at 45 meters per second behind the train. All right, so we still have our train out front, moving 40 meters per second. That's our source. Then we have the car driving west also, and they're behind the train. So the detector is moving a little bit faster at 45 meters per second. And we can look at this pretty fast. out of these two, which one we expect to have a bigger effect? Well, the car is going faster, so that's probably going to have a bigger effect than the train. So the car is moving towards the train, so we expect that to make the frequency go up. The train is moving away from the car, so we expect that to make the frequency go down. But because this car is moving faster, the frequency going up is probably going to have a bigger effect than the frequency going down. So we can already guess that our frequency should be above 650 hertz. But let's actually do the math and try this out. So frequency detected, again, 650 hertz, 343 meters per second, 343 meters per second. Well, I'm just going to be lazy and not write units. All right, so detector in the numerator. So the detector is going 45 meters per second. The source in the denominator, the train, is going 40 meters per second. Is the sound messing up? It may have been the internet dropping out for a second. It's pretty obnoxious. It occasionally drops out for a little bit. All right, so the detector in the numerator, the detector is moving toward the source. Yeah, just let me know if something got messed up and you need me to talk about something again. I can look back at that. All right, so the detector moving toward the source. Because the detector is moving toward, I expect that to make frequency go up. Yes, the source is always in the denominator and the detector is always in the numerator. All right, so frequency goes up, so I expect a big numerator to get a big frequency. And the source is moving away from the detector. So away from, I expect frequency to go down. And to make a smaller fraction, I need a bigger denominator. Yeah, the source is always in the denominator. Detector is always in the numerator. You can kind of think of it as a ratio. It's frequency per speed of the source, detector per speed of the detector. Sorry, I keep getting messages that I have to check to make sure I'm not missing anything important. And again, make sure we use parentheses for our numerator and denominator, something like this. So we have a parentheses for a numerator, parentheses for a denominator. You are important, but if one of the principals is trying to put out information, it might be something that's like really urgent that I have to take care of immediately. And yeah, frequency detected 658.5, yes. Which makes sense. Again, we expected the detector to have a bigger effect, so I expected frequency to go up. But the detector is only going a little bit faster than the source, so I don't expect it to go up by a lot, so this only shifted by 8.5 hertz. So a pretty quick, easy way to test how much sense your answer makes. All right, then 5. The person is driving west at 45 meters per second in front of the train. So now our car, the detector, is in front of the train at 45 meters per second. And then our source, the train itself, still going 40 meters per second after the car passed it. So I can substitute in detected frequency, 650 hertz, 343 meters per second, 343 meters per second. So again, detector always in the numerator, so the detector speed is 45 meters per second. Source always in the denominator, so the source is moving 40 meters per second. Now, again, detector, numerator, the detector is moving away from the train. So away from the train, I expect that to make the frequency go down. To get a smaller number, I need a smaller numerator. And you might be able to hear my cat meowing, because he's the neediest thing ever. So away from minus the source, the train is moving toward the car. So I expect the frequency to go up. In order for the frequency to go up, I need to subtract in my denominator. Smaller denominator, bigger frequency. So the detected frequency is 639.3 hertz. Any questions on the warm-up? So if you have any questions, post them now. And then the next thing, I'm planning on answering some kind of simple questions about the quiz. I don't intend to actually work through anything fully, but if you want some hints or clarification, find the question and I can help a little bit with that. The cat's a boy. Yeah, if you're finished with the warm-up, take a picture of it and post it in Google Classroom. Again, make sure your picture is clear where I can actually read it. Try to do one picture per page, otherwise it's hard to read. You can upload more than one, and yeah, it'll be a free warm-up grade. All right, 2GI. All right, so 2GI is one of them. If you have any other ones, think of those now also. I don't need your name on it because it's getting posted in Google Classroom under your name. Actually, I take that back. Actually, so you don't try to use the same one, I want you to put your name and pin at the top. I changed my mind. Put your name and pin at the top of each of these assignments. Only for the name. You only need to put your name and pen. Everything else you can do in pencil. So 2G, there's definitely questions about 2G. Are there any other questions? Or are the rest of them okay? I personally liked really 3 and 4. Freeman Dyson actually recently died. They probably went to turn in the assignment. I just want the name and pen, so that way you can't reuse the same paper if you meet with someone. I guess if they were really good at photoshopping, they could change. Okay, so 3A. Alright. 3A, 4B1. One and three. One through 4. 4B, 1 and 3. 3A. 3. Alright. I could imagine photoshopping it. It might be kind of obvious though, based on how people take the picture. If they take a really good picture, it would be easy to Photoshop. If they take a bad picture, it would actually be pretty hard to. See, the funniest thing I find about the Plague, even though you say it's not a joke, is have you ever played that game, Plague Inc.? It used to be a Flash game, but now you can play it on on any mobile device. I pretty much always would start out my virus in China, and then it spreads, and it actually spreads. Like every map I look at is pretty consistent, and part of me is like, in a weird way, like, oh man, it's not made it to Greenland or Madagascar yet, so it's having the same difficulties that I had. Yeah, China was always a really good place to start off in that game because it had a large population. Yeah, but if you start in Greenland, it's a small population. So if you start in China, you can get a lot of really points really fast. All right, so let's look at the quiz then. Is there a tabletop game? That sounds interesting, a tabletop game based on that. I'd play it. Some people are just that lazy that they would try to use someone else's paper or picture. All right, so let's look at this. Let's see. I think the first one people were talking about was 2G. 3 and 4 were definitely intended to make you think a little bit outside the box, so it's probably not just you. I intended those to be a little bit more where you had to think. So, 2G. All right, so we're talking about sending out radio waves. So yeah, we send out radio waves to large clusters. This is actually a thing. This proposal was in like the 80s. They didn't have the technology for it yet, but we could actually do this now. Sending out a 10 billion watt radio signal towards the M13 galaxy. That's 22.2 thousand light years away. Light travels at 3 times 10 to the 8th meters per second. Light year is the distance light travels in a year. Thinking is the best part. I don't necessarily like thinking about physics all the time when I'm on break, but I do definitely like doing math and thinking. All right, so first of all, let's kind of... Actually, yeah, let's look at this. So normally whenever we're thinking of light spreading out or sound spreading out, we think of it spreading out in the shape of a sphere, right? So we imagine the sound source and it's spreading out in the shape of a sphere in all directions. And we're looking at the surface area of a sphere. $60 hours over a break? No, I'm probably pretty close to that number. Maybe a little bit less. I also did other things like playing around with Excel. By the way, the picture, my avatar, it's actually a code. If anyone deciphers it, I'll give them bonus points. It's pretty simple, nothing crazy. All right, so normally we expect this to spread out as a sphere. That's our approximation that we're doing. But in reality, if we send out a really focused beam, it's going to make more of a shape like a cylinder. So when I'm looking at a cylinder, we expect it to kind of spread out like this. And then as it goes further, it's eventually going to look like this. So what's this shape that's spreading out? Yeah, when I finish talking about this, I'll look at 2F, all right? You need other things before you get to 2F, though. Okay, so it's spreading out in the shape of a circle. Now, we have our equation. The intensity is going to be, well, the 3D shape is a cone, but a cone is a stack of a bunch of circles. So the actual wavefront is an expanding circle outwards. Looks like a lizard eating something. So we have intensity is going to be power divided by the surface area of the thing that's spreading out. So for 2F, this is spreading out like a sphere, so that's our equation that we have normally. So that intensity is going to be power divided by the surface area of a sphere is 4 pi r squared. But for G, it's spreading out as a circle, and the area of a circle is going to be pi r squared. So that's GI. Yeah, so 2F, you're just putting it into our normal equation. This is the equation dealing with the sphere. So is the mic cutting in and out, or you can actually hear it again? I guess the mic might be out of... Can anyone hear this right now? Okay. So 2, now we're still looking at intensity is going to be power divided by surface area, but the shape expanding out is a circle instead of a sphere, so our intensity is going to be power divided by pi r squared. We all okay on the rest of 2, like 2A through F? Probably the hardest thing about 2A through F is you have to get the amount of years into seconds. What is 2D? How many years? I like 2D because you can do a lot of math or you could do no math. The galaxy is 22.2 thousand light years away. A light year is the distance light travels in 1 year. So if this is 22,000 light years away, 22.2 thousand light years, so 22,000 light years, 22,000 light years is equal to 22,200 light years. So how many years would it take? Right? Yeah, 22,200. Because it's 22,200 light years away. So it would take 22,200 years for light to get there if it travels at the speed of light. So 2F, or 2E, yeah, it's going to be there and back, so it's going to take twice as much time for 2E. Who is A? Because, yeah, that is correct. I can make it more interesting. I have a Excel spreadsheet that pops these out. So yeah, so for 2F power, so 10 billion watts. How much is 10 billion watts? Yeah, I'll give Andrew some bonus points. He might have to remind me, though. So yeah, the one before, it's the fastest we could receive a return signal. So yeah, it would take more than that amount of time, but the fastest we could possibly get a return signal would be they hear it and immediately respond back. So that's the lower limit. So 10 billion watts is 10 times 10 to the 9th watts, or just 10 to the 10th watts. One E. You really need to do 1D to do 1E. I would suggest drawing out a picture. You definitely have to draw out a picture of that. It's going to be similar to one we did in our classwork. I don't think I'm going to do 1E for you. I want to see if you can try to figure that out. The 10 billion watts, that's just for 2 in general. Let's see what other ones. 3. Let's just do 3A first. Oh, yeah, radius. G2. So this radius right here for G2, I think is what you're talking about. You are going to have to use some trigonometry. So this goes out 22,200 light years. But this spreads out in a 10-degree angle. So we're trying to figure out this value here is our radius. Our radius is opposite, so sine theta equals opposite over hypotenuse. So you are going to have to do a little bit of trig there. Opposite is the radius divided by the hypotenuse is 22,200 light years. And again, you're going to have to put light years into meters. I'll just do all of 3A. Let's just do all of 3A. Because there's a few things in there that I could see messing you up. Is that what we solved for on C? C, yeah. How far away it is in meters. Yeah, so you could just use what you put. So instead of this, you could just use what you have in C. So this right here is equal to part C. right, so 3. So Freeman Dyson, he actually just recently passed away. The guy actually only had a bachelor's degree in physics, and he drastically contributed to physics and just barely missed getting a Nobel Prize. But yeah, he proposed a lot of these things that are called megastructures. So he wanted to build these large structures around the sun to collect all the energy coming out of the sun. One of the earlier structures we might actually build if humanity actually survives for the next few hundred years would be to build what's called a Dyson ring. So you have a large solar power ring of just a ridiculous number of individual satellites converting the sun's energy into electrical energy. We're going to say it orbits at 10 million kilometers from the center of the sun and blocks about 0.005% of the light escaping from the sun. The satellite is 30% efficient at converting solar energy into electrical energy, pretty close to what really top-end solar panels can do today. In addition, the sun puts out 1.384 times 10 to the 30th joules every hour, and it would take about 2 times 10 to the 30th joules of energy to completely disassemble the planet Mercury, because of course we want to dismantle Mercury. What has it done for us? The benefit of putting solar panels so close to the sun is they will have a much greater intensity of solar radiation than a solar panel on Earth. What is the power the sun emits in watts? So this would be a type 2 civilization. This right here, what I'm talking about, this would put us past type 1. A Dyson ring like this would probably put us at like a type 1.2, 1.3 civilization. But yeah, a full Dyson sphere would put us at a type 2 civilization. So 1 watt, first off, we need to know the definition of a watt. 1 watt is equal to 1 joule per second. But we're given the sun puts out 1.384 times 10 to the 30th joules per second, or joules per hour, I mean. So we need to put this hour into seconds. So I have 1 hour. I should know this. I'm mostly Irish, but I have no idea if it's St. Patrick's Day. 1 hour is 60 minutes. Get the hours to divide out. And then 1 minute is 60 seconds. Or if you remember, you could have just gone 3,600 seconds in a minute. Yeah, I'm not wearing any green. I guess I could go put on my green shirt. All right, everyone get that? All right, so 2 wants to know the intensity of light on a 1 square meter solar panel in the Dyson sphere. I mean, this is our class time. So intensity, we're going to assume that the light spreads out in a perfect sphere, which is actually a really good approximation. This is like the one time this is a really good approximation for what happens. The light just spreads out evenly in all directions from the sun. So the power is what we just got before, is that 3.844 times 10 to the 26 watts at a distance of 4 pi. And our radius, we're a distance of, where does it say it? Yeah, 10 million kilometers. 10 million is times 10 to the 6th. This is million. But we need to put kilometers into meters, so this needs to be times another 1,000 in order to get meters. And then we need to make sure to square our radius. You can rewatch this in tutorials. I'm planning on having tutorials tomorrow at 1, where I'll have another stream and you can ask specific questions about the homework. But yeah, everyone else can watch this later and they'll see the comments scrolling by, and so they can tell like what questions were asked and what I'm answering. So yeah, you can go back through and rewatch these. We'll get an intensity of 305,895.8 watts per meter squared. This should be this is 3A1, 3A2. 3A2, yes. The homework is posted. I didn't give very hard homework. It'll be due tomorrow at midnight. Well, tomorrow at 11:49. And then so 3A3. How large would we have to make the solar panel on Earth, on average 150 million kilometers from the sun, in order to absorb the same amount of solar energy absorbed by 1 square meter of the solar panel in part 2? So, we need to find the intensity on the surface of the Earth. So that intensity is going to be the same power from the sun, 3.844 times 10 to the 26 watts. But the power is spreading out over a much larger area now, because now we're a distance of 150 million kilometers from the sun, times 10 to the 6th, times 1,000. Let's make sure we square that radius. And we're going to get a much smaller number, 8.61 watts per meter squared, which is why if we ever built a Dyson sphere or something like this, it's why we would put it so close to the sun. You'd get 305 kilowatts per square meter as opposed to just under 9 on the surface of the Earth. And then this number would actually be lower with things like the atmosphere and the fact that there's nighttime on Earth. So we are getting nothing compared to what we actually could be getting on the, like, really close to the sun. So This is actually asking how large we would have to make the solar panel. We really just need a ratio of the two. Notice how these are both watts per meter squared, watts per meter squared. So this is how much power I get in that 1 meter squared. So I want to figure out how many of these I would need. It's just going to be a simple division question. So I need to get 305,895.8 watts per meter squared. But I'm only getting 8.61 watts per meter squared. And so we'll see we need to get something like 35,528 panels. But each panel is 1 square meter, right? Each number 2 intensity of light on 1 square meter. So if I need 35,520 panels, that means I need 35,520 square meters, which is kind of crazy. Your calculator is probably not broken here. Let me type in, let's do number 2 for you. Let me show you how I would put that in my calculator to make sure you're doing it well. So 3.84 times 10 to the 26th divided by 4 pi times so notice a few things. So 1, I put parentheses around my entire denominator, and I put parentheses around the part of my denominator getting squared. So parentheses, parentheses, square. And then we have this number divided by, did I mess that up? Divided by 8.61. There's a chance no, I got a slightly different number here. I don't know what I did differently this time. But yeah, I still got 355,527. Oh wait, no, I wrote that wrong. That's what it says in my paper, 528. And then, intensity of power on the Earth, did I do that one wrong? This one's now 150. Oh yeah, I did do that one wrong. So, yeah, I must have put something in there wrong. So 1,359.5. So not as crazy of a number then. It's still going to be way less efficient though. So only 225, but still a lot more of them. 225 panels. which is going to be 225 square meters. Yeah, 225. So let's look at 4. I think that was all the questions that you had on 3. That was the, yeah. About one thing I would say is make sure for the later questions, 0.005% is equal to 0.005 divided by 100. Make sure you put that into an actual decimal form. All right, so number 4, LIGO, Laser Interferometer Gravitational Wave Observatory, uses one laser beam that is split in 2 to detect gravitational waves created by merging black holes like millions or billions of light years away. Yeah, you're going to use that in 3B, yes. The laser beams travel at a speed of 3 times 10 to the 8th meters per second, so the speed of light. They have a frequency of about 2.182 times 10 to the 14th hertz. The laser beam is split into 2 beams that travel perpendicularly along a 4-kilometer long path. They hit a mirror and reflect back. And this is actually a really small interferometer observatory. They actually have plans of putting these things in space and having them like hundreds or millions of kilometers away using 3 different satellites to do this. So yeah, this is actually a really small type of these observatories. They're trying to make really huge ones of these. So the hint here for B1 and B3 is kind of in that picture. If you look on the picture for 1, the 2 waves go out and then they return at the exact same time, and so they're going to be perfectly in phase. 2, if I want the waves to cancel each other out, what is that picture going to look like? Is that picture going to look like 1, or is the picture going to look like 2? All right, so when the waves cancel out, this is going to look like 2. So when everything returns in phase like this, this is going to be normal operations. So we're not detecting any gravitational waves. And by the way, this is actually so insanely sensitive that they can tell when a freight train is going by like 5 miles away from them. It's pretty crazy. So yeah, this is normal. But in order to get these to cancel out, I'm going to need one of these to shift. Something like this. So this one is going to be doing the exact opposite. Intensity watts per meter squared. So So I want these to line up like this. How much did I have to shift the wave over? And actually how I drew this, I shifted over this one now that I think about it. Let's kind of look at this point here. So this point is right here. So this point here is equal to this point here. But this point used to be where this started at. All right, so it's half of a wave. So what is the minimum distance needed for one mirror to move in order to completely cancel out the other wave? Well, we would need this to move by 1/2 of a wavelength. So if this shifts over by half a wavelength, then everything is going to completely cancel out. So once you find your wavelength in A, all you have to do is do half of a wavelength. All right. So 3 wants to know the minimum distance one mirror would have to shift before the recombined waves again reach a maximum brightness. So the mirror keeps shifting over, so this top wave is going to look the same as before. So these points are still all at the same place for these two. Actually, let's draw these as squares or something. And yeah, this is going to be destructive interference for number 2. All right, now we need to shift this wave all the way over to where now it starts here and it goes up and down. So this is where the wave is, but we need it to line up again with this. So how much did we shift this wave over? How many wavelengths was that? All right, so yeah, that's one full wavelength. So we would need to move one of these mirrors one full wavelength. It's not 0 because it doesn't return back to where it is. At 0, they would constructively interfere, but we want to know how far this thing would have to move until it constructively interferes again. So 0 would be correct. 0 would constructively interfere and make a really big wave. But the problem is it's asking what is the minimum distance one of these mirrors would have to move in order for the recombined wave to reach a point where the recombined wave again reaches its maximum brightness. So we're waiting, we want to shift this over until the next time it reaches maximum brightness. Because we could also shift this by 2 wavelengths would accomplish the same thing, or 3 wavelengths. So 1 is the answer to this question, but I could shift by any number. So yeah, you could, if it's 0 wavelengths, that would be maximum brightness also. Just like this one would be 1/2 until it reaches the maximum destructive interference, but it would also happen at 3/2 or at 5/2. And by the way, these wave things we're talking about, this is actually sort of similar to the fundamentals of quantum mechanics. If you've ever heard quantum, quantized, you can only have so many sets of answers. It's either 0, 1, 2, 3, 4, 5, 6, or 1 half, 3 half, 5 halves, 7 halves, 9 halves, things like that. And then I'm not going to do 4 or 5 for you because you could just kind of look at that. It's just a ratio. 5, you're going to see really small numbers. It's actually a really small portion of a piece of hair. But in reality, it doesn't even have to move this far. So we're talking about things like this can detect movements that are like 100,000th of the width of a hair. It's actually absolutely insane. B2 is destructive interference and B4 is constructive interference, yeah. Yeah, quantum computers use this. It's a little bit more complicated. It's quantum entanglement. So that's much further into quantum mechanics. But just seeing how these numbers are quantized, they can only be a certain number. That's quantized quantum mechanics. It's a similar type thing. Do we convert our wavelengths based on hair length? Yeah, you could do that. Yeah, you could convert it based on a hair length. Just use the unit 1 hair length equals 0.1 millimeters. Just make sure millimeters, you need to put millimeters into meters because our answers before were in meters. All right, so that's about the amount of time I expected to spend on that. So the quiz, just finish it up, write your name on each page, take a nice clear picture of that and post it on Google Classroom, and I'll grade it from there. Everything I'm talking about today will be due at the end of tomorrow. There are the homework assignments. I haven't really gotten to that yet. I'll probably post an announcement and make those due by Friday or something in a similar way. But yeah, I haven't made a complete decision on that yet. So right now you should open your textbook, go online, find the textbook, and I'm going to start with Chapter 16, number 57. Chapter 16, number 57. Class like this, I'm planning on doing it every other day. Yeah, and you can leave. You don't have to be here this whole time. It's good because you can ask questions about it. But if you have to go somewhere, you can always check back, and hopefully people actually post the timestamp so you can skip around and kind of find the easier and harder parts. Yes, you can use a piece of paper to work on this, and then you'll take a nice clear picture of the piece of paper and turn that in. We're going to look a little bit at notes right now. Where was that? I had this pulled up. So we're going to look at something called beats. These are also posted on Google Classroom. All right, so one thing we can do are called beats. It's when we have two waves that are really close to the same frequency, but they're slightly different. So let's say you have one that's 100 hertz and another one that's 101 hertz. So what we're going to see is the waves are really close to being together, but one is going to have a slightly higher frequency than the other, so we'll see moments in time where they line up perfectly, and we get really big constructive interference, and we hear something that's really loud. But then the waves are slightly out of phase, and so we'll reach a point here where one is at a amplitude, one is at a crest, the other is at a trough, and they're going to cancel out. And then they'll get loud again, where it's really loud here, and then it'll get quiet again here. So this is really similar to what we did in class that time, where you were walking around trying to find the quiet spots in a room. It's not quite the same, but it's a similar concept where you have parts where it's going to constructively interfere and parts where it destructively interferes. And it'll sound like a beat. You'll hear the actual noises going through it. So I actually made a video to kind of show this. I don't know how well it's going to sound on here. You can always play it at home. All right. So this first one is actually too low to actually be heard. You might be able to hear some things in the background. Where is this? Get a different piece of paper. So our equation we're going to see here, the question should be posted under 317 homework on Google Classroom. And then they're in your textbook that you used to take notes from. All right, so we're going to see the equation. The frequency that we hear from a beat is going to be the difference in the two frequencies. So frequency 2 minus frequency 1. Now, frequency can't ever be negative. That's why we have an absolute value here. So this first one, we have one of these is 11 hertz, and the other one is 10 hertz. So the frequency of that beat is just going to be the difference of those. So we should hear a 1 hertz beat. Right now, we're not in the textbook, actually. When we do our questions, it's going to be chapter 16, and then you can click on the chapter. So here, if you want to see me do it real fast, you should be able to get to your textbook. You should be able to see something here. Scroll down to 16. So we're in chapter 16, but we're going to go down to problems and exercises. Is anyone still having trouble finding that? Find the textbook. So you can go to your Google Classroom. All right. I would suggest, I'm on this one. I would suggest click on your classwork tab. Here, let's move this a little bit. So click on the classwork tab. That way, when you go on the classwork, you can scroll all the way down to the bottom pretty fast. And then online textbook is what we're looking for under class information and resources. Some of this is review. Some of this is Doppler effect we've already talked about. The only new thing that's going to be on the homework is this that we're talking about right now, which are beats. But again, look at the math we're doing. 11 minus 10 equals 1. So not a whole lot of new things. There's going to be a little bit of Doppler effect, a little bit of math with waves. And again, we'll have a tutoring session probably tomorrow at 1 if you have questions on that. So let's play this video. You won't be able to hear this one, but we can see the wave pattern. I made this on Audacity. You can see the two waves shifting in and out. And we can see when they're out of phase, it gets really quiet here. When they're in phase, it gets really loud here. So we can't hear that one. This one we should be able to hear though. So now we have a 361 hertz sound, and we have a 360 hertz sound. So I expect to hear a 1 hertz frequency. And again, 1 hertz is the same as saying 1 per second. So I expect to hear 1 beat per second. So you hear it kind of go, wom, 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 wom. So it did that 1 time every second. But now I could move these a little bit further apart. So I can move them to 360 and 362 hertz, so the frequency of the beat. We have a 362 hertz tone and a 360 hertz tone. So this is going to be 2 hertz, or 2 beats per second. So we're going to hear this one is going to be a little bit quicker. It's going to go whoa, 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 like once every half a second instead of once every second. All right, we can separate these a little bit further. So if I go a little bit further, then now I'm at 360 and 370. So this thing is going to have 370 minus 360. So we expect to hear a 10 hertz beat. So we're going to hear 10 of these every second. Yeah, hertz is anything amount per second. So the number of hertz is going to be the number of beats per second. Just like hertz could be waves per second or cycles per second. So here, this is going to be 10 beats each second. So they're going to happen really fast. And my cat is invading my setup. So you heard that one, 10 beats per second, so it was going really fast. And yeah, another thing for musically inclined people, if you're trying to tune relative to someone, you can actually tell how close or how far you are away from them. If you're really out of pitch, you're going to hear a lot of beats really fast. If you're really close, you're going to hear longer times between the beats, really low frequency. So you can kind of listen to these noises to tell how fast, like how far off you are from them. If it's getting more and more frequency beats, you're getting further and further away. Lower and lower frequency beats, you're getting closer. The cat already ran off. He was climbed up here. He's kind of wild at the moment. All right, so now we're getting a lot closer. So now we're trying to see, this is like we're tuning our instruments. We get really close. Now we have a 360.1 hertz, and the other one is at 360 hertz. So we're going to hear 0.1 hertz. So 0.1 beats per second. Or if I want to get this into period, my period is going to be 1 over frequency. So it would be 10 seconds per beat. Right? Because 1 divided by 0.1 is 10. So this is going to take a really long time to repeat itself. So this is going to last a little bit longer than the other ones. All right, and if you couldn't hear that very well, I know I'm playing from a speaker out into my living room into a speaker on my iPad. So if you can't hear it, then just play it for yourself and you should be able to actually hear it. Lightning and thunder, not quite how lightning and thunder works. Lightning is a really high current that superheats the air and creates plasma, so it like rips electron apart, and it's the electromagnetic force of the plasma slamming back together that creates thunder. Yeah, you didn't know I was the first person to make Sandstorm? It got stolen from me though. It's actually, my YouTube channel was about codes, and so I actually had some like really weird sounding ones that use similar type things to that. But yeah, she got used to it. Alright, so just a little quick demonstration. So now we can actually do some of these. So is everyone able to find 57 in your textbook? Yeah, and again, if you have to go, just go and you can come back and watch the rest later. We're almost done. I'm only planning on going through 4 of these real fast. Most of them are pretty straightforward. Alright, so 57. Hope you're prepared for some really difficult math here. A car has 2 horns, one emitting a frequency of 199 hertz, the other emitting a frequency of 203 hertz. What beat frequency do they produce? Chapter 16, right? So we're on 16.10. All right, so number 57, again, our equation is just frequency of the beat is going to be the absolute value of the difference of the 2 frequencies. So I have, what were the two? 203 and 199 hertz. 203 minus 199. So we get a beat frequency of 4 hertz. And again, the other ways we could write this would be like 4 beats per second. Or I could get the amount of time. So period would be 1 over frequency. So I would get 0.25 seconds per beat. So a quarter second for each beat. Hard math, I know. Subtraction, really, really hard. Beats per second. I guess as long as that's not intending to say something else. You don't even need to write beats per second. You can just write 4 hertz. So you don't have to write beats per second or BS. So the next one, we're going to do 60. All right, so 60. You can't see it on here. Twin jet engines on an airplane are producing an average sound frequency of 4,100 hertz with a beat frequency of 0.5 hertz. What are their individual frequencies? All right, so I know the beat frequency is equal to the magnitude of the difference in the two frequencies. I know the beat frequency is, they just said 0.5 hertz is equal to the difference in the frequencies. Average frequency, that's going to be right in the middle. So that's, what was it again? 4,100 hertz. All right, so they're 0.5 away. So frequency of 1 is going to be, subtract 0.5, right? 4,000, 099.5 hertz. And frequency 2 is going to be 4,100.5 hertz, right? So they're 0.5 apart, so I add 0.5 to one and I subtract 0.5 from the other. No one sees a problem with that. Not gonna do a gaming stream. What beat frequency would these two produce? So is that going to be a 0.5 hertz? So we want 0.5 hertz different between these. So that means we're looking at 0.25 hertz. So 4100.25 hertz and 4099.75 hertz. So if we average these, the average of these two values, if we add these two up and divide by 2, we're going to get 4100 hertz, which is good. And then our beat frequency, it would just subtract the two of these, we would get 0.5 hertz. So that checks out. Alright, so the last two I was planning on doing were number 30 and 33, just a little bit more Doppler effect practice. And then your homework really shouldn't be too bad after that. If you just try it, you'll see it really shouldn't be too bad. So now we're moving on to chapter 17. So now we're on 17.4. Yeah, so it has to be, they have to be 0.5 hertz away from each other, and they have to average to 4100 hertz. So 17.4, we're doing Doppler effect. So frequency detected, the frequency heard, is the frequency of the source, the frequency that was made, times speed of sound plus minus speed of the detector divided by speed of sound plus minus speed of the source. Well, so in this one we could do guess and check, or we just realize that our average has to be this, and the difference between them has to be this. So I know I have to go from this average, I know I have to do one that goes up by 0.25 hertz from our average, and this one has to go down 0.25 hertz from our average. So that's one way of looking at it. I need a difference of 0.5 hertz. This number needs to be in the middle. So if I go up by 0.25 and I go down by 0.25, then the difference will be 0.5, and this will still be my average. Is that a little bit better? Yeah, I mean, it all goes back to this equation. I would suggest not rigidly using this equation a whole lot, especially if you're trying to find one of the frequencies. Just realize, hey, if this is 4 hertz, I either need to go up by 4 or down by 4, or if I'm trying to maintain the same average, I would go up by half the amount, go down by half the amount of the beat. Yeah, half the beats hurt and you add and subtract it from the average. That way your average stays the same. And because you added half the beat and subtracted half the beat, you end up with a difference that's equal to the full beat. Exactly. All right, so 17.4 is just a little bit more Doppler effect practice. So the last two I'm planning on doing is just, again, 30 and 33. So 30, oh, I didn't change it on here. So go to chapter 17, problems and exercises, and we're looking at 13.4, number 30. All right, so what frequency is received by a person watching an oncoming ambulance moving at 110 kilometers per hour and emitting a steady 800 hertz sound from its siren? The speed of sound on this day is 345 meters per second. And B, what frequency does she receive after the ambulance has passed? All right, so it doesn't explicitly state it, but the person is just watching the oncoming ambulance. So they're probably just standing here stationary. The ambulance is moving towards them. I'm going to draw the ambulance over here. It really doesn't matter. You could put the ambulance over here and moving to the right, or over here and moving to the left. As long as the ambulance is moving toward the person is the only thing that the question is really telling us about this. And it's putting out a source of 800 hertz. So again, just like our warm-up, frequency detected, at least for part A, is going to be the frequency of the source, which is 800 hertz, times the speed of sound. They said on this day the speed of sound is 345 meters per second, sorry. 345 meters per second. Again, we're always going to have the detector in the numerator. The person is the detector, the thing hearing the sound. So our detector isn't moving, so 0 doesn't matter if I add or subtract 0. And then the source, the ambulance, is moving 110 kilometers per hour, right? Does it matter to convert kilometers per hour to meters per second? It does matter. Meters per second, kilometers per hour. So we can't add that, right? So we are going to have to convert this. We can't just put in that 110. All right, so let's go through and actually find this out. So we have 110 kilometers per hour. So let's get rid of kilometers. So I have 1,000 meters in 1 kilometer. We want to divide by kilometers because we want to get that out. So now we have meters per hour, but I want to get rid of hours, not equals to, times 1 hour. I want to put hour in the numerator to cancel out hour right there. 1 hour is 3,600 seconds. Either that or do 60 minutes in an hour, 60 seconds in a minute. And we should end up with not 30.556 meters per second. All right, so we can substitute this in. So 30.556 meters per second. I wouldn't round so much, especially because it's an intermediate step. That's why I kept so many of these digits, because I'm going to be substituting this in. All right, and then the source moves toward the detector. So again, moving toward the detector, I expect that to make frequency go up. In order to make frequency goes up, I need a small denominator. So we should get frequency detected in part A is going to be 877.7 hertz. Which makes sense. We expect a bigger frequency when the source is moving towards the detector. All right, and then after this, now for part B, what is the frequency when the ambulance has passed? So now they're listening over here, still at rest, but now the ambulance has driven past them. So frequency detected is going to be that 800 hertz times speed of sound on this day is 345 meters per second. So in our final answer, it doesn't matter as much. Just keep like 3 or 4 non-zero digits and that should be fine. If you put more digits, I'm not going to count off. I'm not going to go crazy about sig figs or anything. So the detector, always in the numerator, the detector is still at rest. The source is the ambulance, which we found was going at 30.556 meters per second. But now ambulance is traveling away from the detector. So ambulance moving away from the detector, I expect this to make frequency go down. In order for frequency to go down, I need a big denominator. A big denominator means a small fraction. And we should get a number smaller than 800 hertz. All right, hopefully Doppler effect is kind of making more sense by now. Don't overthink the plus or minus. We're really just looking for the words toward or away. Toward makes frequency go up, away from makes frequency go down, and then we decide whether we add or subtract to make that effect happen. So if there's no questions on that one, hopefully that one went well. The last one we're going to talk about is 33. So be reading 33 and be thinking about it. Alright, so 33. A spectator at a parade receives an 888 Hz tone from an oncoming trumpeter who is playing an 880 Hz note. At what speed is the musician approaching if the speed of sound is 338 meters per second? So again, just a real simple sketch would be good. We have the person hearing, the detector is listening, standing next to the parade. The source, the trumpet, is moving towards the person. They're emitting an 880 hertz sound, but our detector is hearing 888 hertz. So again, frequency detected equals the frequency of the source times the speed of sound plus minus the speed of the detector divided by the speed of sound plus minus the speed of the source. So this one's a little bit different. We're given the frequency detected. The person hears 888 hertz, but the trumpet is only making an 880 hertz sound. They give us the speed of sound on this day is 338 meters per second. Again, numerator is the detector. The detector is not moving, so we can just ignore this. And we're trying to find how fast, what speed is the musician approaching. So we're trying to figure out how fast that source is moving. So explain what instrument I played when I was in middle school and high school. Alright, so let's multiply our denominator over. So 888 times 338 plus speed of sound of the source. I played a small tuba. Isn't that a euphonium? 880 times 338. Wait, what did I do? Sorry, I wasn't paying attention when I wrote this. So this is moving toward the observer. So toward the observer, I expect frequency to go up. Because I expect frequency to go up, I need to put a minus sign in my denominator. So I got distracted by the trumpet. What, this whole thing is just a conspiracy to try to get us to think trumpets exist? Alright, so I could divide this 888 over, so 338 minus speed of the source is 880 times 338 divided by 888. Then I can add this over and subtract this over. So 338 minus 880 times 338 divided by 888 is equal to the speed of the source. Clarinets are alright. I like sound woodwinds can make, but I obviously like the trumpet more. 33.5 is a bit high. Something went off there. It should be more. I got 3.05. They're also marching. If a person was marching at 33.5 meters per second, they're going as fast as a car on the freeway. Well, the piano is a string instrument. Any questions on 33 or anything else? Because this is all I had planned to go through, and we've been here for 2 hours. And yeah, just yeah, the piano is kind of string and percussion. Yeah, it uses a hammer that hits a string, but the noise you hear is the actual strings resonating. And we'll actually get to stringed instruments. That's the next thing we're going to talk about: string instrument and also any other sound instruments. When am I going to post the stream? So the stream is just going to stay on YouTube. I'm probably not going to put it on Google Classroom. I'm just going to leave it here, and you can just put under the class today. You can put that in there. Yeah, things coming up. I have to wake up early. I tried not to start this too early. That's why I started at like 10:30. I figured that's enough time to sleep. 16.9, I'm letting you do that on your own. It should be pretty straightforward. 16.9 shouldn't cause a lot of issues. So yeah, things that are going to be due, turn in your warm-up by tomorrow night. Turn in this homework by tomorrow night. I did half of the newer problems. The 16.9 problems should be really straightforward. Those are just using speed as distance over time, or speed of a wave as wavelength times frequency. There's only about one on there that I think might cause even somewhat of a struggle, but those should be pretty straightforward. So yeah, turn in your warm-up, turn in the take-home quiz, and turn in your homework by tomorrow night. And I do plan on, if nothing else changes, we will have a tutorial session from about 1 to 2 tomorrow, unless we get any sort of direction about times that we have to do things. So any questions before I end the stream? Alright, yeah, everyone, have a good day. Otherwise, just check into Google Classroom, and I'll keep posting everything there. And if you have any questions, you can either ask on Google Classroom, or you can email me. I'll actually be looking at emails a lot more while I'm at home. So if you have a specific question, just ask me over email or ask it in Google Classroom. My sponsor is physics, the thing that everyone wants to do every single morning. So enjoy it. And have a good day.